Welcome to today's session. In this video, we'll explore LeetCode problem number 690, Employee Importance. This problem requires us to calculate the total importance of an employee, factoring in their own importance as well as the importance of all their subordinates. We'll break down the problem, discuss the best approach, and implement the solution step by step. Let's dive in. In this problem, we are working with a data structure that represents a company's employees. Each employee is defined by three attributes: an ID, which is a unique integer identifier for the employee, an importance value, which is an integer representing how important the employee is, and a list of subordinate IDs, which includes the IDs of employees who report directly to this employee. The task is to calculate the total importance of a specific employee. This includes the importance of the employee themselves as well as the combined importance of all their subordinates, both direct and indirect. The input will consist of a list of employees, where each employee is represented in a structured format with their ID, importance, and list of subordinates, and an integer ID that specifies which employee's total importance we need to compute. The output of the problem will be an integer that represents the total importance value of the given employee, including the importance of their direct and indirect subordinates. For example, consider the case where the input includes three employees. Employee 1 has an importance of 5 and has two subordinates, employees 2 and 3. Employee 2 has an importance of 3 and no subordinates, and employee 3 also has an importance of 3 and no subordinates. If we are asked to calculate the total importance for employee 1, the result will be the sum of their own importance, 5, plus the importance values of their subordinates, 3 and 3, making the total 11. To break this down further, employee 1's importance is given as 5. They have two direct subordinates, employee 2, with an importance of 3, and employee 3, also with an importance of 3. Since neither employee 2 nor employee 3 has any subordinates, their total contribution is simply their own importance values. Adding these together, the total importance for employee 1 is 5 from themselves, plus 3 from employee 2, and another 3 from employee 3, resulting in a total of 11. Now, let's consider another example. Here, employee 5 has an importance of -3 and no subordinates. If we calculate the total importance for employee 5, the answer is simply -3, as there are no other subordinate contributions. Looking at the second example more closely, employee 5 has a negative importance value of -3, which is valid within the constraints of the problem. Since they have no subordinates listed, there are no additional values to add to their total importance. Therefore, the final result is just their own importance value, which is -3. Now, for a third example, imagine employee 2, who has an importance of 3 and one direct subordinate, employee 5. Employee 5, as we already know, has an importance of 2 and no additional subordinates. To compute the total importance for employee 2, we take their own importance, 3, and add the importance of employee 5, which is 2. This yields a total importance value of 5. In this third example, we calculated the total importance for employee 2 as 5. Employee 2's own importance is 3, and their subordinate, employee 5, contributes an additional 2. This gives a total of 5 when summed together. The problem also comes with several constraints to keep in mind. For example, the number of employees will range from 1 to 2,000, and an employee's importance value can range from -10 to the power of 5 to 10 to the power of 5. Each employee's ID is guaranteed to be unique within the range of 1 to 2,000, and there will always be exactly one employee matching the given ID in the input. Additionally, the employee hierarchy is structured such that there are no cycles. This means no employee can be their own subordinate, whether directly or indirectly. Finally, it's important to note that an employee's list of subordinates may be empty, as we saw in some of the examples. To solve the problem of determining an employee's total importance, including their own and their subordinates' importance, we need to carefully evaluate the structure of the input. Each employee is described by their ID, their importance score, and a list of their subordinates. Our goal is to calculate the total importance for a given employee ID by traversing this hierarchical data structure. One of the approaches we considered is the brute force method. The idea here is straightforward. Repeatedly loop through the list of employees to find the given employee and recursively calculate the importance for all their subordinates. First, we search for the employee with the given ID, then add their importance to the total. Next, for each subordinate listed under this employee, we repeat the process by searching for their details in the list and adding their importance. However, this approach is inefficient. Since searching the list for an employee takes n time, and this is repeated for each subordinate, the time complexity can grow to n squared in the worst-case scenario. This inefficiency makes the brute force approach less suitable for large datasets or deeply nested hierarchies of employees. The brute force method, while simple, has significant drawbacks. It becomes increasingly inefficient as the number of employees or the depth of their hierarchy grows. To address these inefficiencies, we considered an optimized approach using a hash map. The key insight here is to pre-process the employee list into a hash map where each employee's ID directly maps to their corresponding employee object. This pre-processing step allows us to perform lookups in time instead of repeatedly searching through the list. Once the hash map is created, we can use either depth-first search (DFS) or breadth-first search (BFS) to traverse the hierarchy and calculate the total importance. Starting with the given employee ID, we add their importance to the total and then recursively, for DFS, or iteratively, for BFS, process their subordinates by quickly accessing their details from the hash map. This approach has a time complexity of n, where n is the number of employees, with n time spent building the hash map and another n to traverse the hierarchy. While this method requires additional space for the hash map, it eliminates the inefficiencies of the brute force method and is much better suited for larger inputs. Both DFS and BFS are viable strategies for traversing the employee hierarchy once the hash map is built. The time complexity for both approaches remains n, as we still need to visit each employee once. However, there are some trade-offs between the two. While BFS processes nodes level by level using a queue, DFS uses recursion to explore deeper levels first. In this problem, DFS aligns naturally with the recursive nature of the task, making the implementation clean and intuitive. Additionally, DFS allows us to directly manage the hierarchical structure without requiring an explicit queue, which simplifies the code. Given these considerations, we decided to use the optimized hash map approach combined with DFS as our primary solution. This strategy avoids the inefficiencies of the brute force method and leverages the hierarchical structure effectively. The pre-processing step with the hash map eliminates repeated searches, and the recursive nature of DFS matches the problem's requirements well. While BFS is an equally valid alternative, DFS offers a more elegant and straightforward implementation here. The only trade-off is the additional n space required for the hash map, which is a worthwhile cost given the significant improvement in efficiency. The key breakthrough in solving this problem was recognizing that the brute force approach repeated expensive searches for employee data, which could be avoided by using a hash map. By pre-processing the data into a hash map, we transformed the problem into a simple traversal task. This optimization not only reduced the time complexity from n squared to n, but also made the solution scalable to large datasets. With the hash map in place, the choice of traversal method, whether DFS or BFS, became a matter of preference, with DFS being particularly well suited due to its natural alignment with the hierarchical structure of the problem. This efficient and elegant approach ensures that our solution performs well even for large inputs with deeply nested hierarchies. In this problem, we aim to calculate the total importance of a given employee. This involves not just their own importance value, but also the importance of all their direct and indirect subordinates, determined recursively. To solve this, we're provided with a list of employees, where each employee is represented as an object with three key properties: their unique ID, their importance value, and a list of IDs representing their direct subordinates. Additionally, a target employee ID is given, and our task is to compute the combined importance for that specific employee. The first step in our approach is to process the employee list by creating a dictionary that maps each employee's ID to their corresponding object. This mapping allows us to quickly access any employee in constant time, which is crucial since the input list isn't sorted. Without this, searching for an employee by ID repeatedly would be highly inefficient. Once we have the dictionary in place, the next decision is choosing the traversal method to compute the total importance. Both depth-first search, DFS, and breadth-first search, BFS, are viable options here, but we'll use DFS for this tutorial because it naturally aligns with the recursive nature of the problem and is straightforward to implement. To do this, we define a recursive function called DFS that takes an employee ID as input and calculates the total importance for that employee and their subordinates. Here's how the function works. First, we retrieve the employee object using the dictionary we created earlier. Then, we initialize a variable, total_importance, with the employee's own importance value. For each subordinate in the employee's list of subordinates, we recursively call the DFS function on their ID and add the result to total_importance. Finally, the function returns the accumulated total importance. To get started, we simply call the DFS function with the target employee ID, and it will handle the recursive calculation for the entire hierarchy, returning the final result. This problem's recursive nature arises from the way an employee's total importance depends on the total importance of all their subordinates, forming a tree-like structure. To handle this efficiently, we use a dictionary to map employee IDs to their objects, ensuring that lookups take constant time. This significantly optimizes the algorithm, as we avoid repeatedly searching through the input list. While both DFS and BFS can traverse the hierarchy effectively, DFS aligns more naturally with the recursive structure of the problem, making it an intuitive choice. In terms of data structures, the dictionary is our primary tool for fast lookups, while the recursion stack, either implicit or explicit, manages the tree traversal for DFS. This combination of efficient lookups and a traversal method tailored to the tree structure ensures that our solution is both elegant and efficient. Analyzing the complexity of this approach, the time complexity is O(n), where n is the total number of employees. This is because each employee is visited exactly once during the computation of their importance. For space complexity, it is also O(n), stemming from the dictionary we use to store employee data and the recursion stack used during the DFS traversal. Now, let's consider some edge cases. If an employee has no subordinates, their total importance is simply their own importance value. In the case of a disconnected graph, where the target employee ID is missing from the input, the algorithm should handle this gracefully by either returning 0 or raising an error. Lastly, we don't need to worry about circular references in the hierarchy since the problem guarantees a tree structure, which means there are no cycles. With this foundation, we can move forward to implementing the algorithm. The pseudocode starts by mapping the employees by their IDs into a dictionary. Then, we define the DFS function, which calculates the total importance recursively and finally returns the result for the target employee. The implementation concludes with the DFS function call, which is initiated using the input target ID. To see this in action, let's walk through an example. Suppose the input consists of 3 employees, employee 1 with an importance of 5 and subordinates 2 and 3, employee 2 with an importance of 3 and no subordinates, and employee 3, also with an importance of 3 and no subordinates. The target employee ID is 1. First, we create the employee map, which associates each ID with its corresponding employee object for fast lookups. With this setup complete, we begin a DFS traversal starting from employee ID 1. The initial importance is set to 5, corresponding to employee 1's own importance value. Next, we recurse into employee 1's subordinates. The first subordinate is employee 2. Since employee 2 has no subordinates, its total importance is simply its own value, which is 3. This value is added back to employee 1's total importance. Then, we move to the next subordinate, employee 3. Similar to employee 2, employee 3 has no subordinates, so its total importance is also 3, which is added to employee 1's total. At this point, we've processed all of employee 1's subordinates. Combining these values gives a total importance of 5 plus 3 plus 3, which equals 11. This final value is returned as the output, representing the total importance of employee 1, including all their direct and indirect subordinates. And that's how the algorithm solves the problem efficiently and systematically. The solution calculates the total importance of a given employee, including their own importance and the importance of all their direct and indirect subordinates. First, the input list of employees is transformed into a dictionary, employee_map, for quick access by employee ID. This avoids repeatedly iterating over the list, improving efficiency to O(n). A depth-first search, DFS, is used to calculate the total importance. The DFS function is defined to recursively compute the importance for an employee and their subordinates. For each employee, the function retrieves their importance and adds the importance of their subordinates, obtained by recursively calling DFS on each subordinate ID. The recursion ensures that the importance of all direct and indirect subordinates is included. Finally, DFS is invoked with the given employee ID, returning the total importance. The solution is efficient and handles edge cases like employees with no subordinates or invalid IDs gracefully by leveraging the dictionary lookup and recursive structure. Here, we start by defining the employee class, which serves as the blueprint for our employee objects. Each employee instance has three attributes: ID to uniquely identify the employee, importance to store their importance value, and subordinates, which is a list of IDs representing the employees they manage directly. The constructor initializes these attributes when creating a new employee object. Next, in the solution class, we define the getImportance method. This method takes a list of employees and the ID of the employee whose total importance we want to calculate. To facilitate quick lookups, we first build a hash map called employee map, where each employee's ID is the key, and the corresponding employee object is the value. This mapping allows us to efficiently access any employee by their ID. Finally, we call a helper method named DFS, short for depth first search, passing in the map and the given ID to compute the total importance recursively. The DFS method is where the recursive depth first search is implemented. It begins by retrieving the employee object corresponding to the given ID from the employee map. The total importance is initialized to the importance value of the current employee. Then, we iterate over the list of subordinates for this employee. For each subordinate, we make a recursive call to DFS, passing the subordinate's ID. This ensures that we calculate the total importance for all the employees in the hierarchy below the current employee. The results from these recursive calls are added to total importance. Once all subordinates have been processed, the method returns the accumulated total importance. This recursive approach ensures we account for the importance of every employee in the hierarchy, including indirect subordinates. In the employee importance problem, we are tasked with calculating the total importance of a given employee, including their own importance value and the importance of all their subordinates, both direct and indirect. Each employee is represented as an object with three attributes: an ID for their unique identifier, an importance value that denotes their contribution, and a subordinates list containing the IDs of their direct subordinates. For example, in the given input, employee 1 has an importance value of 5 and 2 subordinates, employee 2 and employee 3. To efficiently look up employees by their ID, we first create an employee_map dictionary. This map associates each employee's ID with their corresponding object, allowing constant time access to any employee's details. Here, the employee_map is initialized with employee 1, employee 2, and employee 3, which sets the stage for solving the problem using a depth-first search approach. To compute the total importance, we start a depth-first search, DFS, from employee 1. We retrieve their object from the employee_map, which gives us their importance value of 5 and their subordinates IDs, 2 and 3. We initialize total_importance to 5, representing employee 1's own importance, and then recursively process each subordinate. For employee 2, we retrieve their object, note their importance as 3, and since they have no subordinates, we return 3 as their total importance. Similarly, for employee 3, we retrieve their object, find their importance is also 3, and return 3 because they too have no subordinates. Finally, we aggregate the results, employee 1's importance of 5, plus the importance of employee 2 and employee 3, which are 3 each. This results in a total importance of 11 for employee 1. The final output for this example is 11. In a different example, employee 1 has an importance value of 10 and one direct subordinate, employee 2. Employee 2, in turn, has an importance value of 3 and one subordinate, employee 3. Employee 3 has an importance of 2 and no subordinates. To solve this, we again start by creating the employee_map, associating each employee's ID with their object. This allows us to quickly retrieve employee 1, who is our starting point for the DFS. We find that employee 1's importance is 10 and proceed to process their subordinate, employee 2. For employee 2, we retrieve their object, which shows an importance value of 3 and a subordinate ID of 3. We initialize total_importance to 3 and proceed to process employee 3, their only subordinate. For employee 3, we retrieve their object, find their importance as 2, and since they have no subordinates, we return 2 as their total importance. Returning to employee 2, we aggregate their importance of 3 with the importance of employee 3, which gives a total of 5 for employee 2. Finally, we return to employee 1, where we aggregate their importance of 10 with the total importance of employee 2, resulting in a total of 15 for employee 1. The output for this example is 15. In another scenario, employee 2 is the focus, with an importance value of 3 and one subordinate, employee 3. Employee 3 has an importance value of 4 and no subordinates. To calculate the total importance of employee 2, we first construct the employee underscore map to retrieve the details of employee 2 and their subordinate. Starting the DFS with employee 2, we set total underscore importance to 3 and process their subordinate, employee 3. Employee 3's importance is 4, and since they have no subordinates, we return 4 as their total importance. Aggregating this with employee 2's own importance, we get a total of 7 for employee 2. The output for this example is 7, which represents the total importance of employee 2, including their own importance and the importance of their subordinate, employee 3. The time complexity of the solution is determined by two major steps, pre-processing and depth-first search, or DFS. First, the pre-processing step involves creating an employee underscore map, which is a dictionary that allows constant time lookup for any employee by their ID. This process iterates through the list of employees exactly once, so it takes n time, where n is the total number of employees. Next, we have the DFS traversal, which is used to calculate the total importance by exploring the hierarchy of employees starting from the given ID. In the worst case, this hierarchy forms a tree-like structure, and the DFS visits each employee exactly once. For each employee, accessing their data in the employee underscore map is an O1 operation, and iterating through their subordinates takes time proportional to the number of subordinates. When we consider all employees, the total traversal time is proportional to n. Therefore, the DFS step also has a time complexity of O(n). Now, combining the pre-processing step and the DFS traversal, the total time complexity of the solution becomes O(n) plus O(n), which simplifies to O(n). This means the algorithm scales linearly with the number of employees in the input list. Moving on to space complexity, the solution requires O(n) space in total. Let's break this down. First, we have the employee underscore map, which stores all the employee objects with one entry per employee. Since there are n employees, this storage requires O(n) space. Additionally, the DFS traversal uses recursion, which adds frames to the call stack. In the worst-case scenario, where the hierarchy is deeply nested like a chain, the recursion depth can reach n. This means the memory used by the call stack is also O(n). Adding up the space required for the employee underscore map and the recursion call stack, the total space complexity becomes O(n) plus O(n), which simplifies to O(n). Let's compare this with a brute force approach. A naive solution would involve repeatedly searching the list of employees to find the one with the given ID and summing their importance recursively. Searching the list for an employee by ID takes O(n) time, and this is done for each employee, leading to a total time complexity of O(n) squared in the worst case. By using a dictionary for constant time lookups, our solution optimizes this to O(n). In terms of best, average, and worst case scenarios, the time complexity remains O(n) in all cases. Whether the hierarchy is flat, partially nested, or deeply nested, the algorithm processes all employees exactly once. However, the deeply nested hierarchy results in higher space consumption due to the increased recursion depth. Finally, let's solidify our understanding with a mathematical proof of the big O notation. Since each employee is visited exactly once during the DFS traversal, and every subordinate list is iterated through exactly once, the total work done is directly proportional to the number of employees. This confirms the O(n) time complexity. Similarly, the total space usage arises from the employee underscore map storage and the recursion depth. Both of these scale linearly with the number of employees, which validates the O(n) space complexity. This linear growth in both time and space ensures that the solution is efficient and scalable, even for large datasets. In this section, we'll examine some common mistakes to avoid when solving the employee importance problem. First, a frequent issue is ignoring the recursive nature of subordinate importance. If you only add the importance value of the current employee and overlook their subordinates, the result will be incomplete. Subordinates may themselves have additional subordinates, and their importance values must be included in the total. Next, inefficient employee lookup is another pitfall. Repeatedly iterating through the list of employees to find the one you need results in a time complexity of O(n squared) in the worst case. Instead, using a dictionary for constant time lookups is much more efficient. Finally, while the problem guarantees a tree-like structure, it's still a good practice to safeguard against cyclic relationships. Assuming cycles cannot exist might work for this problem, but in real-world scenarios, you should implement cycle detection to avoid infinite loops or incorrect calculations. Another common mistake arises when using DFS without tracking visited nodes. If accidental cycles are present, revisiting nodes during recursion can lead to infinite recursion or double counting importance values. Even though cycles are not part of this specific problem, being mindful of tracking visited nodes is good practice for similar challenges. Additionally, assuming that all employees have subordinates can lead to unnecessary recursive calls or errors. Employees with no subordinates should act as base cases in your recursion, terminating the process early and improving performance. Failing to account for this can result in inefficient or even incorrect implementations. Now, let's discuss some interview insights that can help you excel. A key data structure to use is a dictionary or hash map that maps employee IDs to their corresponding employee objects. This ensures O(1) lookups and significantly improves efficiency. When it comes to choosing between DFS and BFS, both approaches are valid. DFS often feels more intuitive for recursive calculations, while BFS can be clearer for iterative solutions. Understanding the trade-offs and being flexible based on the interviewer's preferences is crucial. It's also important to clarify constraints early. Confirm whether the input guarantees a tree structure, no cycles, and valid IDs. This helps avoid incorrect assumptions during implementation. Lastly, consider space complexity. DFS may use O(n) stack space for deep hierarchies, while BFS also uses O(n) for the queue. Be prepared to test and discuss edge cases such as having a single employee without subordinates or extremely deep hierarchies. Let's explore related problems and alternative approaches. Problem number 104, maximum depth of binary tree, involves a similar recursive DFS approach to calculate a cumulative property depth in that case, compared to importance here. Problem number 733, flood fill, and problem number 200, number of islands, use DFS or BFS to explore connected components, which is analogous to traversing the subordinate hierarchy. Problem number 133, clone graph, also deals with graph traversal, making it another useful practice problem. Regarding alternative approaches, recursive DFS is intuitive and straightforward to implement but uses stack space proportional to the hierarchy depth. Iterative BFS, on the other hand, avoids recursion issues by using a queue to process employees level by level, though it requires additional code to manage the queue. Topological sorting, while not necessary for this problem, might be useful in related scenarios where processing order matters, but here, the hierarchical structure simplifies the traversal. The key insight to solving this problem effectively is to focus on accumulating importance values by traversing the hierarchy. Efficient lookups using a dictionary and avoiding redundant computations are critical. Additionally, optimizing for edge cases and ensuring good performance under large inputs will not only lead to a correct solution but also demonstrate your ability to handle real-world constraints. This approach ensures clarity and efficiency, both of which are essential in an interview setting. Great job! To summarize, we used traversal techniques like DFS or BFS to solve the employee importance problem efficiently. We covered both time and space complexities and discussed when this approach is most useful. Thanks for watching, and don't forget to like and subscribe for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!